Hello students. So we are in chapter 6 and we are studying root locus. Okay. So far we have seen some of the examples basically, and based on those examples we do have some ideas now what is root locus, and hence now we can talk about general purpose. So earlier we took some examples and we tried to plot the root locus, but now we will go general purpose and see in a way the method how to plot it, which all things are which all things are important, so that we will see. And for any complicated open loop transfer function, we should be able to draw, if not exactly, at least roughly we should be able to draw the root locus. So that's what we will do now. Let's take the general case and assume T naught S, which is the open loop transfer function. Open loop transfer function is T naught S, okay, and this T naught S is, as I mentioned yesterday, so any open loop transfer function can be written as S plus Z1 S plus Z2 to S plus Zm divided by S plus pole 1 S plus P2 till S plus Pn. We can write it like this one, where we know that Z1 P1, so Zi Pi are complex. Okay, so they could be real also. They could have they could be purely real number or purely imaginary number, or could be combination of the two. Yeah, so but they are complex number in general. Okay, okay. So and also m is less than equal to n. Yeah. This is required. M should be less than equal to n, otherwise you have to transfer function as such will follow this, like numerator will have less number of the order of the polynomial, and the numerator will have less, denominator will be large number. Yeah, so otherwise, always we can like simplify into this one, means that if it is otherwise, if m is greater than n, then you can write it as a constant plus something like this one, which will have now m less than equal to n, right? So finally, whatever this form, you will get it. Yeah. And also the most of the real life systems are basically which has m less than equal to n only. So you can also see, for example, let us say you have a spring damper system, that's it, like this, K, you see here. Then if you apply a force F and there is a displacement x, you can write equation K plus Cx dot equal to Ft here, so Ft. So if you take Laplace transform here, you get K plus Cs, it will be Kx plus Cx dot, okay, so Xs equal to Fs. Now if you take F as input and this as output, then transfer function S is given by xs over fs, which will be equal to 1 over k plus cs. And hence you see that polynomial here is of a higher order than this one. The numerator can have higher only when if fs is input, if the force is input or ft is input and xs is output. And in this case transfer function will be k plus cs. And in this case you see numerator has the higher order than this one. But then it does not, then is a problem is not difficult one, very trivial problem then. Actually, if x is given, if for you input is known, f is automatically known and it is precise. Whatever the value here you give, you will get that. So this is a not challenging problem. Also, there is no need to control basically. What it means that regardless of what x you give, you put k times x plus you differentiate of that x and you get the unique solution here automatically. So there is no like a, you don't like this is the like in depending on what you give x, immediately f will be known. Yeah, and if you can move precisely the way if you want, the f, you cannot control f, meaning that whatever the x is given, f is, you can calculate according to that. But if you other way around, if you have force applied, then calculating x is difficult. You have to solve the differential equation. But in this case, when this is output, x is input, you are not solving any differential equation. You are just differentiating x and putting here, and you will get ft. Yeah, so that really means the transfer function you get for a differential when you have a differential equation. Yeah, so there you have to like let us say if you want x to behave a certain way, then you have to accordingly you have to plan f or input f that way. You know. Here also you are doing the same thing, but here this the problem is much simple. Why simple? Because there is no differential equation here. Yeah, so it is very straightforward. However, when it involves differential equation, this becomes difficult to solve, and hence the control system and all those things comes into picture. So, so basically, this gives you one example why the order of this will be greater than order of this one. Okay, just in case you wonder why it should be like that. Okay, so anyway, so we have this open loop transfer function, and as I said earlier, z1, zi are the zeros and the pi's are the poles. Of course, when we say zeros, understood that these are for open loop transfer function. Okay. Now next is what we have to do. Now we have to predict the roots of the characteristic equation of the closed loop, the corresponding closed loop transfer function. Okay, that's the idea. Okay, so predict the roots and hence predict and plot. And how you plot? On the z plane we plot. We trace all the points on the s plane which can be roots of the characteristic equation of the closed loop transfer function. it could be the predict, of course those will be based on the k value. We change the, for different k value we have different. So in S plane, so if we are seeing like, if we have like this one, this is the, let us say this is how the a root locus looks like, meaning that really means this point, all points could be the roots of that characteristic equation. However, the k value will be different at different places. Yeah, so that's what it means. Okay, these things we know already. Okay, so the idea is you can predict the roots of the characteristic equation of the closed loop system if you know the open loop transfer function, which is given like this one. And how do you do? The first thing is the steps we will follow. Okay, so step one. Step one, first thing we will do is mark the zeros and poles on the S plane. First thing you have to do. Yeah, so we have been doing. So how will you do? So depending on where Z1, Z2, Z3, zeros, you say like this one, it could be here. Yeah. So 0 can also be a complex. Yeah, so those are also possible. So 0 here, this kind of things also possible. So first thing you are going to do is mark them. Okay. Now then poles also you have to mark. Yeah, so poles. So poles will be cross. This can also be the complex conjugate, and all those things you are going to mark. And then based on that, now you can also predict few things. So step 2 will be plot root locus on the real axis. Okay, on real axis, it is very easy to plot. Why? This is because it is symmetric about the real axis. Yeah, this is the real axis, right? So all the things, whatever you are getting, the points are symmetric about the real axis. Hence, it is very convenient. And convenient, what is convenient? So one of the things that you have to apply in this case is what we studied yesterday. And how you can find out? Yeah, basically, you know that the angle of all those things, right? So angle of S plus Z1 plus and so on, plus angle of S plus Zm minus angle of S plus P1 minus angle of S plus P2 and so on, minus angle of S plus Pn, all should be equal to 180 degree. Okay, 180 degree plus minus 30 degree. So it could be 180 degree, or you can write like that, or minus 180 degree. So I will say plus minus 180 degree. Yeah, so those are same. Either you take plus 180 or minus 180. The value will be the same for all, sine, cos, tan, whatever. So basically has to be equal to this. This it has to follow. So let us say we have we have here 1, 2, 3, 4, 5. In this case 1, 2, 3, 4. Okay, doesn't matter. We can have more crosses here. Let us say like this one, so that we have number of crosses or the poles are more than number of zeros. Why? Because of this, because m is less than equal to n. Now if we have to plot here, how, let us say this is how the zeros and poles looks like. So these are the zeros, and these are the poles. Let us say it looks like this one. So how will you plot it? Yeah, so if we have to satisfy this equation, angle made by s plus z, so now we are plotting where? Plot on the real axis. So let's take point here. We can test it. Which is the right to all of these points, zeros and crosses on the real axis? If we extend the from here to here, if you take the line, all of them, if you join this point to this point, cross to this point, this is test point P, okay? So from here to here, all of them are making zero angle with that. So that really means what happens? 0 plus 0 plus 0 minus 0 plus minus 0 minus 0 will be equal to 0 only. Hence, here it's not possible. Here, actually, the root locus will not be there. Otherwise, this angle, total angle, we get 0 only. Now look at this one. At this, all of them are 0, but this one, see here from the, now test point is P here. The angle it is making is 180 degree. So what do we get? This is a 0, so you get 180 degree plus 0. For all others 0, it will be 0, 0, 0, 0. And here for all the poles also is 0. If you connect from here to here, the angle is 0 only. Connect from here to here, angle is 0. Only this point, only this one has 180 degree, because you have to measure it from the horizontal line, which is going right, going to the positive x direction. So here 180 degree. So what you get? In this case, you get 180 degree, meaning that point here to here are basing on the root locus. Yeah. So here to here is the root locus, and you know that at the cross it is k equal to 0, and at the zeros or the where the k equal to infinity, right? So that we know there's a k equal to infinity when where the zeros are, and when there's a cross, there k equal to 0. That we have studied already. So this like this. Now look at this one. What happens? For all of them it's 0 till here. Now the point P is here now. Okay. For all these points, angles are 0. Okay, now one thing. There are these also. Yeah, so earlier I did not mention here. These points are also making some angle here. So see here, right? So, but what happens is one angle is like this and another is like this one. So total, if you see this plus this become 360 degree. So in a way, both of them nullify basically. Yeah. So hence there is no effect. Okay. So let me draw again and we will resume. Okay. So let's draw same as this one only. Okay, so we had one point here, then we had here, cross here, 0 here, 2 crosses, cross one more here, 0 here, and 2 cross here. Okay, randomly we have like this one. Now the idea is to draw the root locus. So as we studied here, so we know that as far as the, like let's say this point, so one thing we forgot this one, so we also have to include this one. So I just look at this only. So for all these, they make 0 to this point. This is making 180 degree. Yeah, so this is 180 degree. So for this, we can write 180 degree. And for this, we have 0 degree, 0 degree, 0 degree, 0 degree. So all of them are making 0 degree. What about this? So we have like this. Yeah, so angle will be like this. And similarly, for this one, angle is like this. So if let's say angle is this phi, and this will be 360 degree minus phi. Yeah, so hence we can find out what is that meaning of that. Similarly, for if you see here, okay, so this is what, yeah, angle is like this one. Let us say is called theta 1. Yeah, and similarly from here to here. Now this is the complex conjugate. So exactly below this. Yeah, same distance from here, same distance like this one. Yeah, so roots, the zeros and the poles either will be a real number which will lie on that axis, or will appear in the complex conjugates, meaning that there will be pair of 2 and which will be symmetric about this line, right? So that's what it means. Okay, now this if that is okay, so if this is theta 1, then this will be 360 degree minus, so this angle, so this angle is 360 minus 5, similarly 360 minus theta 1. So if you look at this point, total angle we can find out. And how will you find out? First we take all the zeros. So zeros, if you write here 360 degree minus phi plus phi, 2 zeros done. Then for this one is 180. So write 180 degree, and this already taken care of. Then this is 0, this 0, so plus all 0. This 0 and this 0. Now we have to subtract the angle for all the crosses in all the poles. Okay, so for this one is 0. For this is also 0, this 0, this 0. So minus 0, minus 0, minus 0. So all these crosses take care of. For these ones, for this we write minus theta 1. For this minus 360 degree plus theta 1. Yeah, equal to what angle? You can see that. See here, 360 is there. This phi gets cancelled. Theta gets cancelled. 360 get cancelled. Even if 360 don't get cancelled, 360 if you add or subtract 360, it doesn't make any difference, right? Finally, your answer is 180 degree, and hence it tells you that this point is on the root locus because this satisfies this angle condition. And regardless of which point you take, always from here to here it will be satisfied, and hence this is on the root locus. Yeah. Similar analysis you can do here, and we will find that for this one it is 180 degree. This also had 180 degree. If you are here, then what happens? This cancels out. Why? Because this is going to plus side and this is going to be a minus side, right? So minus side. So you have 180 degree. Everything will be same, and I mean not the same. Basically, you have to work this way, And you will realize that here it's not possible because 180 degree coming from here, but here minus 180 degrees and becomes 0. So this is not possible. Here again it becomes possible. Here it's not possible. Here also becomes possible. And here we have to see, here also it's possible only. Here also it's possible only, but there will be more than that. What you find in this case is, sorry, here it will not be possible because this again, okay, sorry about that. So what you are doing is, the first one come from the right, yeah, take the, you have to join the odd number pairs basically. So this is the first pair, connect this. Second, you leave it. Third, you connect it. Fourth, you leave it. Fifth, connect it. Sixth, you leave it, and so on. Why? Because of the angle. Yeah. So if you do that, automatically on the real axis you are already completing the root locus. So this comes from this angle condition. So plotting on the real axis is very, very easy. One thing also you remember here, that the root locus will start from the pole, so cross is the pole, and it will move towards the 0. So start means here where it will be k equal to 0. So k equal to 0 is at the pole, and k equal to infinity at the 0. Yeah. So direction meaning that k is increasing. Yeah. So k is increasing from 0 to infinity. So similarly you can draw it here. So it goes like this one. At the end also it will extend and towards the infinity. Yeah. Okay. So what curve will join them? That is not known yet. That we have to explore. Yeah. So only we are talking about on the real axis. So on the real axis we can draw like this. Also note here the last point. There is a pole here, and we are assuming that it will be continued to the infinity. So as if there is 1 0 at the infinity. Yeah. So this extends to the infinity. Now this is also known as asymptotes. Yeah. So asymptotes basically means that there is a line which extends to infinity. Yeah. And the actual root locus will be tangent to that line in infinity. So in this case, this one, the one which is going to negative real axis, so that will be counted as one asymptote. Total number of asymptotes also you can find out. So number of the step 3 will be like find out the asymptotes. Now number of asymptotes will be equal to n minus m. So in this case, for example, we have n equal to 1, 2, 3, 4, 5, 6. So we can write 6 minus and number of zeros. So that is 1, 2, 3, 4, 5. So minus 5 is equal to 1. That really tells us that there is only one asymptote, meaning that there is only one line, whether curved or a straight line, that is extending to infinity. That really tells you. So in this case, this will be the line which will be extending to infinity. Whenever you get the odd number of when you have like only one, that really tells you that it should be on the real axis only because of the symmetry. So the root locus will be symmetric. Always it is symmetric about the real axis. Okay, so now we can also find out what will be the angle of asymptotes. So the angle of asymptotes will be equal to, of course, the has to be 180 degree divided by 1. In this case 1. So typically we have 180 degree multiplied by 2k plus 1 divided by n minus m. Why we did 2k times 1, where k will be equal to 0, 1, 2 and so on? Because so that we have the, we can also write plus minus also. Yeah, it's the plus minus also. So here 2k plus 1, because we have to maintain 180 degree, either 180 degree or 180 degree plus 360 plus 360 more, and like that, divided by n over n. That actually divides the, this is the rule basically, and this is also coming from the this like condition. Yeah? So the angle of asymptotes only this is when you have like this, when you have the angle of asymptotes this, only then this is going to satisfy that one. So in this case, when you have only one, you will have one. So we can see also through the example what I mean. So when you have like number of asymptotes equal to 1, so then in that case, what you get? You get 180 degree only, plus minus 180 degree, meaning that the angle in say this is 180 degree or minus 180 degree, the same thing. So this is talking about this, the asymptote is aligned 180 degree to the positive positive x direction, right? So it goes backward. When you have two of them, then you will have plus minus 90 degree. Yeah, so it will extend this way. Okay, we will see that example. So this we can only relate through examples only, because they are coming from the examples and they have to satisfy this also, and hence it is coming like that. So we will see another example to see that. Let's look at the original example. We have been looking at s plus 2 divided by s square plus 1. Yeah. So if we plot here, what we find out, in this case, s plus z1 divided by s plus p1 s plus p2. So here k is there, so k like this. And where z1, we know that simply in this case z1 is, so here if you solve it, we find out that z1 equal to minus 2 and p1 equal to minus I and p2 equal to plus I. So we have these zeros and poles, so we can draw it here, so like this, and we have poles here. Yeah, so we have I minus I, so this is p2, this is p1, and then we have here 0, which is minus 2, like this. Okay, now looking at it, we can draw. Can draw means, see here, first thing what you have to do, have all the roots on all the zeros and the post plotted. So I have plotted. So step 1 is done. Step 2. Now we have to plot on the real axis. The real axis, we start from here. So the first one is basically this. From here, this way will be simply the root locus. Why? Because here, if you see angle from here will cancel out. From here it's 0, so it's not meeting 180 degree requirement. But here, this is 180 degree, and here they cancel each other, so 180 degree. So this is correct. So we know automatically that as far as this real line is concerned, there is no root locus here, but there is a root locus here. Yeah, so that we know. Okay, so step 2 is done. Now step 3, number of asymptotes in this case will be, number of asymptotes will be equal to 1. So why 1? Because this is 2, number of asymptotes is equal to n minus m, which is equal to 2 minus 1 equal to 1. So in this case also we get equal to 1. Now let us say if we had T naught equal to simply T naught S is equal to K times nothing here, just K divided by S square plus 1. And then we wanted to find out how the root locus would look like. Now in this case, for this case, this we have drawn for this one. For this case, we will have simply cross here, there is no 0. And in this case, at this point, no root locus. On the real axis, there is no root locus. Now number of asymptotes in this case will be like number of asymptotes will be equal to, we have 0, m equal to 0, n equal to 2, 2 minus 0 equal to 2. That really means there are 2 points in infinity, or there are 2 zeros in the infinity. Okay, and where are those? We have to find out. And how will we find out? We have to find out the angle. So angle of asymptotes, okay, is equal to plus minus 180 degree and 2k plus 1 divided by n minus m. And what do we get from here? Plus minus and 180 degree. Let's say k equal to 0 we take. Okay, and here 2, what you get? Plus minus 90 degree. Yeah, even if we take equal to k equal to 1, then we get 360 degree. So this was for k equal to 0. Now take k equal to 1, then what do you get? K equal to 1 plus minus 180 degree multiplied by 3 divided by 2. Yeah, so you get plus minus 540 degree, 540 degree divided by 3 divided by 2, and then you get plus minus 270 degree. So that really means actually the same thing, 270 degree, meaning that you start from here to here, it goes here, and then from here to here, so it's actually 90 degree only. So in this case, the k equal to 2 or 3, they will only give you 90 degree only actually. Yeah, so basically what it tells you, there are plus minus 90 degrees the one. Okay, and 90 degree means our the asymptotes has to be somewhere, it will go like this, because this is what the 90 degree is. Yeah, this is 90 degree plus 90 degree, this is minus 90 degree, and hence this is how the root locus will go, from somewhere. From where, we don't know, but this tells you that root locus cannot be on this line. Root locus has to go in the imaginary direction, both plus and minus direction. Yeah, so this tells you. You can guess here where these lines meets. You know that the root locus has to start from here. No matter what, it has to start from here. And when it starts from here, either it can go this way, up, downward. Okay, but what we know that there are two asymptotes and there are two poles here. Most likely it should go from here, it should proceed to infinity. We can also check whether what we have done is correct or not. So just apply the angle rule. So here you have 90 degree, and this one, let's look at a point, this one, right? So from here to here, this is 90 degree, and from here to this point also is 90 degree, right? So from cross to a test point P, 90 degree. So what you get? 90 plus 90, or rather we have 0 minus 90 minus 90 minus 180 degree, and hence it satisfies. So what you see that this line indeed goes to infinity like this one. Here also the same analysis you can do. You can find the root locus in that case. If you have this transfer function, open loop transfer function, root locus will be simply going from here to infinity, from here like this. Yeah. Other way to find out where these asymptotes meet the real axis, we can also find out. And how can we find out? We can find out the real path. So if you find out the sigma asymptote, let's say sigma asymptote, meaning that where it is going to meet the real axis will be equal to, we have P1, P2 and so on. So what you do? You will write real of P1 plus real of minus, all minus, yeah, real of minus P2, yeah, and so on, okay, and divided by n minus n. But this is correct when there is no zeros. Okay, when there is a zeros, then you have to write differently. Okay, so in this case, for example, if you have to take, so I will rewrite here. So sigma asymptote where it is meeting equal to, we can write minus the real of minus P1 plus real of minus P2 and so on. Then we have to say minus real of minus Z1 minus real of minus Z2 and so on, divided by n minus n. Okay, so in this example, let's look at this example where it should meet, and we will find that the real of P1 and P2, both of them are 0. So what we get is 0 plus 0, and there is no Z no zeros, so divided by 2. Okay, so you get 0. That really means that the asymptote meets the real axis at 0. So that really means that this is the asymptotes which meets at 0 here. That's what it tells you. So we get the angle, we get the point where it meets. In this example, if you want to find out where it meets, we will have real of -2, sorry, just a minute. So in this case we get, so real of the P1, P2 are 0, so all 0, plus real of zeros, okay, minus real of, in this case we have z minus 2, and divided by, we get that, and divided by, we have n is equal to 2, m equal to 1, so 2 minus 1, and we get simply 2 in this case. So what it tells you that this is meets this line at 2, so point 2 is here somewhere, right? So here, so it's fine. If you see that this is where it is actually, if you extend this here, it can go a straight line. So this result is not misleading. Actually, it is in line with the meaning of asymptote. So asymptote basically in this case is telling that this is meeting at point 2, but this can meet anywhere basically, like, since this is along the real axis only. Okay, so in a way it is working here also, and here also you have seen. So in a more complicated one also you can see. So for example, if you have three asymptotes, so could be, the example could be, let us say T naught s equal to, now we can have one more, let us say, let's call k equal to, and you have s, then s square plus 1, like this one. Maybe we write s plus 1 here. Okay, so let's write it s plus 1 here, like this. Okay, k over s plus 1 multiplied by this. Then what kind of, then how will you find out how the root locus will be? Okay, so we will apply what we have learnt now. So we have these lines here and s minus 1, so 1 cross minus 1, and here another one, you have I and you have minus I, right? So you have 3 of them. Now what? Number of asymptotes equal to, what do you get? N minus m, and n is 3, m equal to 0 equal to 3. Angle of asymptote equal to plus minus 180 degree, 2k plus 1 divided by n minus m is 3 equal to, what do you get? You get, we have to see all the possibilities. So when you say k equal to 1, k equal to 0, so k equal to 0, possibility is you get 5, 1 is equal to 5, 1, 2, let's call it plus minus 60 degree. Yeah. Now what is the, when you put k equal to 1, then you get others. So you get plus minus and 3 times 180 divided by 3 is equal to plus minus and 3 multiplied by 3 divided by 3 is 100 degree. So plus minus 180 degree. So which is really same. K equal to 2 is going to repeat basically this only. So what it tells you is this gives you phi 3. So phi equal to simply tells you 60 degree. Yeah, then minus 60 degree and 180 degree. Yeah, so all 120 degree apart. So what it tells you, this has to be something like this. But how? We don't know where these points will meet. Yeah, so we can find out sigma asymptote is equal to simply all of them has there is no zeros here, so we get real of 0 here plus real of this also have the real of I is 0, real of minus I is also 0, and then this real of minus 1 is minus 1 divided by n minus m equal to 3. Yeah, so what we get is minus 1 over 3. So somewhere here is going to be the point from where it is originating, and at what angle it is originating. So minus 60 degree. So there is one point, so there plus 60 degree, minus 60 degree, and 180 degree, like this. So this shows you the asymptotes now. Now the root locus has to follow that, so that at infinity these asymptotes are going to be tangent to those root locus, and hence the root locus should go this way. Of course, should start from here and this will follow, go like this one. Yeah, so and it will be symmetric, so go like this, and from here also it should go like this. There are 3 asymptotes you see, and all of them like originating from the poles in this example and going to the infinity, because there are 3 zeros at the infinity. So number of zeros at infinity is equal to n minus m. Right? So since n minus m is also tells you number of asymptotes, and hence it gives you 3, and it goes like this. You can also see here why all this angle had to be, this had to be 60 degree, or this is equally divided 120, 120, 120. This also you can see. Means what is the origin of this equation? This also you can see now. How? Let us say you are looking at a test point which is far away here. Okay, very far away up here, and in that case your this point, the test point P, is so far away that the angle from this cross, it goes like this one. Yeah, and this is 60 degree. Angle from here will also be 60 degrees. So since it is very far away, and these points are close, so all the angle, regardless of from where you are starting, all are 60 degree only, and hence you can add now together, right? So you can say 60 plus 60 plus 60. Yeah, so all the 3 adds up to 180, and this is required equal to 180 degree, right? So and this is the requirement, a test point to be on the root locus, and hence you equally divide that 180 degree in 3 parts. Same thing you can do here. If you are very, very far away, point here, so angle, this angle, what it makes here, so from this point, like this one, what angle it makes is minus 60 degree. From here also, this point also it will be minus 60 degree, and from this point also will be minus 60 degree. Okay, so you add all the three, becomes minus 180 degree, which is required. Similarly, you can do here. Similarly here, on this anyway, these points are since these are symmetric, or it is 180 degree everywhere, regardless of whether you are here also, then also, because they cancel each other. So on the real axis, it is going to cancel each other. However, if you are not on the real axis, then this is, when you equally divide that, then only it is going to meet the condition. Yeah, and hence you have this formula applied, meaning that it simply tells you that all the angles are equally, so there is a equal angle between the two. That's really it tells you. So if there are two asymptotes, then angle between the two will be 180 degree. There are three asymptotes, angle between the three will be 120 degree. There are four asymptotes, angle with the four will be 90 degree, and so on. That's what it tells you. Will be equally divided, so that all the angles are add up to 180 degree. There is one small correction though. This will not look like this one. If you have four asymptotes, if there are four, then 180 divided by 4, so becomes 45 degree. So when you have four asymptotes, then this will look like this. So you will have 45 degree here. But still, it is correct that equal angles between them. So this is 90 degree, this is 90, this is 90, this is 90 degree. But orientation here will be 45 degree. Yeah. So similarly here, if there are two, orientation have to be 90, 180 divided by 2, so 90, so it will go up and down. If there are two, it will go up and down. If there are three, one should go this way, and one this way and this way, and hence you have 60 degree, here 60 degree, it will be like this. 4, then it will go like this, yeah, and then you have 45 degree like that. If you have 5, accordingly we can decide, right? So if you have 5, then it will be this 36 degree, and how it will be? It will be 36 degree here, and 36 degree here, 36 degree here, one will be here, and 72, so another 72 here, and similarly you will have from here to a 72 degree, here to a 72 degree, and so on. So hence 5 of them. Yeah, so these go like this one, and this one, and this one. 5 of them. So and so on. Yeah, so this is the origin. That's why at least you understood, and hence this you can extend it to any number of poles and zeros. With this understanding, we can also actually derive this equation, meaning that at which point all the asymptotes are going to meet. Okay, so this is for this example, this is the open loop transfer function. Okay, so let's delete all those. So this open loop transfer function, what you get here is we can write this one, T naught is equal to K, okay, over, we can simplify, right? So first we expand it, so S cube plus then we get s square, then we get s, and then we get plus 1 in this case. Okay. Now when s is big, when s tends to infinity, this is a large, very very large, that we are talking about when if you go to the infinity, there what you see is the higher order terms will be the one which will be dictating that. They will be dominating. Means, consider here, infinity to the power 3 plus infinity to the power 2. So this is the term which is going to dominate more if s is a big number. So for when s tends to infinity, t naught s, we can write it as k over, and just write in terms of s plus, and we can write 1 over 3 q. Why? That way you can match at least this and this term. How? If you expand s plus 1 over 3 to power 3, you will find s3 plus 3 times 1 over 3 times s square plus 3 times 1 over 3 square times s, and then you have plus 1 over 3 to power 3. This is what you get. So what you get here is q plus s square plus here you get 1 over 3s plus 1 over 9. These compare first term, second term. First, second terms are matching, only the third and fourth are not matching. But if s is very, very large, this you can neglect. So this and this value, this and this are approximately correct. Yeah. So now when s is large, it is like this one. Okay. When s is large, we can also write the closed-loop transfer function, and what we get? The characteristic equation of the closed loop transfer function we can write is 1 plus t naught s is equal to 0. That's what we are going to find out. Yeah, and what we will get is simply, in that case we will get s plus 1 over 3 power 3 plus k equal to 0. Now here, if k is the value of k, in this case we can neglect here. Even if k has some infinity value, let us say, first of all, in the control system the k will be finite, but it's the infinity value. But here, even the power is 3, that means this is much bigger than this one, so this can neglect. So this will be simply s plus 1 over power 3 equal to 0, or simply we get s plus 1 3 equal to 0. This is the equation of, this is a equation of the asymptote. However, remember that which s we are talking about? S we are talking about somewhere here, and somewhere here only, because not all s are being considered. Only those satisfy the angle rule, for example, and magnitude rule, or those who are going to be on the root locus. So s plus 1 over 3 equal to 0 is the equation of the asymptote, where s is somewhere, s has to be very, very large, so s is here, s is here, s is here. So that means if s is there, the line which has to be drawn is from minus 1 over 3. So if s is here, so you draw from minus 1 over 3 to s. S is here from minus 1 over 3 to s. S is here from minus 1 over 3 to s. And hence this point minus 1 over 3 is the point where all the asymptotes meet. Okay. Accordingly, you can also analyze for any number of zeros and poles. Yeah. Remember that this is an equation of asymptote when s tends to infinity. Okay, the s is very, very large. So there, this is how it looks like. Okay. Similarly, for example, T naught s equal to, let us say, if you are talking about 1k over s square plus 1, and in this case we have k, and then we have s. This is as good as k over s square when s tends to infinity, right? And then what you get is s equal to 0, right? S equal to 0 is the point where the asymptote will meet, and hence in this case you have at this point when it is going to meet, and that we have seen. And we know that these are the poles, and hence it will go upward like this one, and the value will be 90 degree. Value will be this 90 degree and minus 90 degree like this one. That you can we have seen earlier also. So minus the 180 degree divided by 2, because there are 2 here n, so hence you get 90 degree plus minus. So plus minus 90 degree, hence you get, and this meets here. Let's take the example of T naught s equal to s plus 2 over s plus 1, then s square plus 1. And we have here s plus 2 divided by, so first of all we can just plot it, and s plus 2 is the 0 here, so minus 2 here, here we have cross minus 1, and then we have here also, here also. So this is I, this is minus I. So we have done this one. The root locus, we know that one root locus will be here. Yeah, why? This is from here we get, this is the first line that joins the two, so hence root locus has to be here. Others we have to see. Okay. Then we have to find out what is the number of asymptotes. Yeah, so number of asymptotes equal to, how do you find out? N minus m simply, where n is 3 and m is 1 equal to 2. So there are two number of asymptotes. Now we have to find out the angle of asymptotes equal to plus minus 180 degree, 2k plus 1 divided by n minus m. So in this case plus minus 180 degree divided by 2, or plus minus 90 degree only. So we know that it is going to be 90 degree. Now third thing is which point. Then we have to write this. For s equal to infinity, write approximate T naught s. That's what we are going to do, and let's write it here. So T naught s approximate will be equal to we get it here, so we write like this: the s plus 2 s plus 1 s square plus 1, and here we can write, we have a k here, remember k here, so k put here. This we bring it down, so we make s plus 2 minus 1, okay, and or you can write like this: k s plus 1, yeah, s square plus 1 multiplied by s minus 2, like this. Yeah, so approximately it will be approximately like 1 over s plus 2 when you have 1 over s plus 2, yeah, and here we have minus 1, so like this one. We are approximating it by this one, and we can do it. When we can do it? When we have the like for example 1 over, we have s minus 1, and we have s 1 plus 2 over s minus, like this, and then we 1 over s minus s to the power minus 1, and 2 over s is tends to infinity, so we can simply, we can do also the Taylor series, for example, and we can get minus 2 over s, basically we get like this, and we if you put it there, yeah, so what do you get from here? So okay, just a minute guys. So what we get here is s inverse, and then we have 1 minus 2 over s only. Yeah, so we can write like this only, or we can write it simply equal to 1 over s inverse, and then we have 2 times s to power minus 2, like this, or simply 1 over s minus 2 over s square. Okay, so here it will not be s minus 2, so it will be 1 over, we can write it like this: 1 over s minus 2 over s square, like this. Yeah. Okay. So it has now we get 1 over s, which is common. So simply we can write like this: k, and then we have 1. Okay, so you can take the s this side, so we can write either 1 plus 1 over s multiplied by s square plus 1 multiplied by 1 minus 2 over s, like this. Okay, so what we see here, the order, the maximum order becomes like s square. So if we work out this one, let's work out. So if we work out here, so this multiplied by this, we get s square plus 1 here, and then plus we get s, and then plus 1 over s. Okay, and then we have to multiply 1 minus 2s. So what we get? We get s square plus 1 plus s plus 1 over s, and minus 2 minus 2s, right? Minus 2s minus 2 over s minus 2 and minus 2 s square. What is important here is s square term and s term, right? So we have s term here, we have s term here and here. Yeah, so those are important, right? So others we can neglect, constant term 1 over s term, because s, when s tends to infinity, we can have this equal to s square plus 1 minus 2, yeah, s, yeah. So it will be like this, yeah, which is equal to s square minus s, yeah, plus more terms here. Okay. Now this one minus 2 term is becomes minus 2 here. Now next will be to write in terms of s plus a square. Yeah? We write in terms of s plus a square such that we get this term. So we are writing like this. So we have s square 2as plus a square is, we are equating that s square minus s plus 1. So what we get is minus 1 equal to 2a, and we get a equal to minus 1 over 2. Yeah. Okay, so this we get equal to s minus 1 over 2 square. That's what we get. Yeah. So this one is nothing. We can write k over s minus like this. Yeah. Now where is the asymptote? If s tends to infinity, s minus 2, s minus 1 over 2 becomes this becomes the equal to 0, right? So s minus 1 over 2 equal to 0, the equation of the asymptote when s tends to infinity. So that means half is here, this is 1 over 2 here. Yeah. So asymptotes, basically what it tells is this is here somewhere. This is the asymptote. Okay. Now, so how does this look like? This is half here. So we know that the asymptotes meet here. What is the angle? 90 degree. Yeah, the asymptote angle is 90 degrees. So here and here. So asymptote is 90 degree, here and here, both 90 degree. And these are the asymptote. Here these two are the poles. So it has to originate from here and it has to meet the asymptote in the infinity, so it will go like this. So this is what the root locus will look like. Okay. So you have one that goes to the 0. The other two will go in this way. Yeah. And this tells you that this one is not stable because this is on the other side, right? So it has the positive real value. Yeah, that's what it tells you. Applying this, we have taken long to explain to find out the value. We could have just applied the formula. And what was the formula? The sigma asymptote is equal to real of this, yeah, real of minus p1. So real of minus 1 here plus real of I plus real of minus I, right? And then we had minus real of minus 2 divided by n minus m. N minus m is 2, right? And what do we get? We get minus 1, 0 plus 0, minus plus 2 divided by 2. 2 minus 1 is 1 divided by 2, half. And hence, we already got half from this. Yeah? So basically, we get half from here. So this is the origin of this formula. This formula actually comes from this one. This is for the small example I took. You can take any number of zeros and poles and you can derive it. Yeah, but this is the idea. Okay, so that is all for today. And in the next lecture we will have further steps. Okay, so I purposefully went slow so that you can understand. I first gave the rule and then we try to explain why those rules are, so, and went very slow so that it is less confusing. It's very important that you understand this one, and then it will be very easy to draw. You can easily see if the system is stable or not for the given open like open circuit. If you have open loop transfer function given, then the system is stable or not, you can find out. So in this case, for the open loop, the transfer function is given, and we find out that it has a positive real part, hence it is not going to be stable. Yeah, so it is very powerful too.